Here you've got your basic lathe spindle. It rides in a taper bearing in the front, and I can't remember the last time I had it apart. I believe there's 2 taper bearings, and they're, I'm probably better off with just grabbing some replacements from SKF. Don't bother with getting ultra precision bearings, whatever the fit is, A, B, C, G, D. As long as it's got a rating, it's probably going to be better what's in here, and the machine is just not accurate enough to take advantage of a really good bearing. So if you're going to change those out, just get the, middle of the road or a pair of cheap bearings, and they're probably going to work just fine. No, I do not have the sizes or the numbers because I haven't replaced them yet, so I would have to measure them and try to find a suitable replacement. I'm not going to buy them from Smithy. Any parts you get from Smithy for this vintage of machine is going to be old stock, so there's going to be no improvements made to them. They're going to be made to the exact crappy standards as it was when the machine first came out. So get them from there if you have no choice, but you're better off making your own for repairs and modifications. It's a 2-speed screw or feed transmission here, and I pretty much keep it in the turning mode. Since I said it didn't come with change gears, it had the basic turning ratio installed, and that's pretty much what I keep it for manual machining. So I'd have a high speed, low speed, and a neutral, which sometimes works and sometimes doesn't. And this is the engagement lever for that. It's normally pointed over here, but it's just easier for me to have it this way. This is where the old control panel was for the stop, off, and reverse switch. Stop, off, start, stop, and reverse switch. And it was just, I didn't need it. So when I did the conversion for a DC motor, it just went by the wayside, and I'll put something else down here. I'm thinking of putting in a voltmeter and ammeter in here, so when I test out tool geometries, I can see what kind of load it's putting on the machine. I have the parts, I just haven't gotten around to making a panel and putting that in. So stay tuned, maybe I'll get to that sometime shortly. What else can I play with? These are my basic knobbies I play with. My speed control, on, off, on. So I got forward, reverse, off. This is a little switch that turns on and off my motors. And this switch here is to raise and lower the mill head. There's no logical pattern to this because this was all done as I went along. So I started off with a treadmill motor and used the controller that came with it. So I needed a reversing switch and a speed control, so I just stuck them in the panel. Then later on, when I started playing with the CNC stuff, I needed a way to shut off the motor drivers so I could turn the handles. If you're not familiar with stepper motors, once they are energized, they are locked. They do not move. That's what they do. So you have to shut them off at the driver, because if you disconnect them at the motor, it burns up the drivers because they're being fed power all the time. And that allows me to turn the handles. But you can't turn them fast because stepper motors act like generators when you power them by mechanically. And it spits juice out the back through the wires, and that goes right back to your drivers. And if you turn it slow, it's okay. You go a little faster, it fights you. And that's the electrons bouncing off the doorways of the driver. And if you turn it fast enough, the electrons will break down the doors and burn up your driver. And that's happened to me twice. Fortunately, the parts for them are cheap. They're just using MOSFETs, IR 44s or something like that, and they're pretty easy to change out. Where else can we go? Since you saw this, you know that another modification I did was take off the original motor and put a DC treadmill motor on. And I started off with one of the smaller 2 horsepower or beer can size motors. And I chopped off the flywheel. Let me go grab that for you. So this came out of the treadmill I bought. I can't seem to get the stuff out of the garbage like everybody else does, so I bought this treadmill for like $50, and I grabbed the controller and the motor out of it, and you can see it's kind of narrow, but it was a good size to fit back in the mounting position on these Smithies, which is right on the other side of the lathe head, and we'll get to that in a couple minutes. Ignore the pulley. This is the only one I had lying around, and I only needed the smallest section of it. But I just stuck it on there, and that provided the drive for the machine. And it was good. It worked fine. But I just wanted something a little beefier, and I happened to score a better motor at the junkyard, or a metal recycler, and they didn't tear it up too badly, so I was able to make that work. So that's the motor I'm using now. But I highly recommend. They're cheap at the right sources. They're easy to work with, and you get your nice variable speeds. The motor is controlled with one of these bad boys. This is a KB Electronics. Model number is KBMG 212D. I will throw that up on the screen. And this is a 4-quadrant regenerative braking reversible DC motor controller. This will run off both 110 volts and 220. It allows you to run the low speed or the low power motors. Treadmill motors are typically rated at 90 volts. Your bigger treadmills and the industrial motors are usually at 130 to 180 volts. So this controller allows you to go both ways. You can do the 90 volt range or the 180 volt range. You can only use, of course, the 180 volt range if you're in the 220 mode, but it allows you to work with a wide range of motors. And there's a lot of settings on here. This board is a daughter board that has preset speed controls on it, so you can have preset speeds for whatever you're working on. I'm not using that. This is a spare I keep around. But it allows you to set braking force, acceleration times, maximum speeds, dead band, a whole lot of neat stuff. So that's what allows me to do stuff like power tapping and neo stuff with the mill head, because it'll stop on a dime if I have it set that way. But my basic variable speeds, and I can get it down to about 40 RPM on my lowest belt setting, and that's usually pretty good for what I usually do. I would like to have or set up a back gear system for it for when I'm swinging some big cast iron, like those big exercise weights. Haven't gotten around to it. But since I haven't needed that badly, I haven't done a back gear setup. So there's that. And when it stops, the regenerative braking slows it down in a controlled manner. I have it set kind of loosely because I don't want it stopping so quick that everything is, getting stressed. I don't need to stop that fast. But you can set it to stop pretty darn fast. Or you can have it ramp down slowly, like I did with the hydraulic press. But I love these controllers. They're, I must have put it away. It's pretty damn robust. I've beat the snot out of it, and anytime this machine's acted up, it's because it's been a loose connection or a motor brush or something went bad. The controller has been top-notch. So I like to keep those around and play with those DC motors. So we addressed variable speed, we addressed higher torque, we addressed getting a lower speed, and that was all done with the DC motor conversion. What other doohickeys have I done? Okay, so this is looking on the right-hand side of my saddle. And it's good practice when you're milling or in doing machining. You lock down the axis that doesn't need to move during the operation, just to keep your accuracy and make the machine more rigid and get less chatter and blah, 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 blah. So they do provide this little lever here underneath the hand wheel, and that would lock my long travel. But to lock the short axis, it had just a set screw in there. And finding the wrench and digging around, and I'm not very organized, I would just not lock the table. It was such a pain in the ass, because I would do that and then I'd forget it's locked and then crank this and put more wear or knock something out of adjustment. And it was such a pain in the butt. So I just came up with this stupid little lever here. I replaced the set screw with a new screw that has just a round barrel on one half, and that is threaded. And then this outside collar here is machined flat also, and the screw goes into there and holds these two pieces together. And it holds them tight enough to where when I pull this tight, I get a nice tight table, but it allows me to take that screw out or loosen it, and this becomes loose here. Then I can take out the screw or adjust it for when I change a gib or for wear. Because if I left it like this, I wouldn't be able to spin it around and put it all together, and I'd have to take this all apart. So this just allows me to adjust by having these two halves be separate. And that goes just with a little piece of rod here that's been bent a little bit to hump over the bedway. And this is all just a piece of metal and bits and screws that's screwed onto the side of the apron here. And it works out pretty good. For the screw, I have either Teflon or some low strength Loctite in there, and that just keeps that bolt snug, so when I have it locked, it stays locked throughout the vibrations on the machine. Because a small machine like this, you're going to get vibrations. So it stays locked, and it's right here, and now with the practice of being able to lock it easily, I get better results. So that was a nice little project. Unfortunately, none of these were really videoed, or if they are, they're bits and pieces that's somewhere on the computer, and if I can maybe get them together, I'll try to separate these and put them up. But this is basically what I've done. What else? Oh, let's go to the motor mount. That's going to be kind of hard to show because everything is going to be in the way. Okay, we got a bird's eye view over the machine, and the original motor and the one I replaced it with afterwards was mounted in something like that position there. And there's a hinge point here, and a plate would come up here, and the motor bolted to the plate, and it had this elaborate mechanism for shifting it, but you could never get enough shift travel to comfortably change the belts. So that was a stupid design. Next, when I put the bigger motor in, I lost some swing room, because if the table's over, I'm going to be bouncing off the bottom of the table, or I'd be hitting the chip tray. So just to eliminate all that mess, and to give me the room over here so I can move the table even farther closer to the spindle head here, I just moved the motor. But the motor was moved down to the bottom of the chip tray. A wide slot was cut in the chip tray and the gear train housing of the machine, which allowed me to feed the belt through both pieces. So the motor sits down here, and it has a pivot plate and mount right here. And when I want to change the belt, I have a foot pedal up front that pulls the motor in, it takes the tension off the belts, and I can just reach around, change the belt position, and let off the pedal, and it's all back to normal. Okay, that's like I said, there's really poor lighting back here, but that is the other motor I've been running, and that's a 180 volt model. I believe it's rated for 2 horsepower, but this is a quality motor, so those are probably closer to 2 actual horses than the 2 little mini horses that you get overseas. The cooling is taken care of by a homemade axial fan that I have on the back there, which is pretty easy to make. I just make a hub that fits over the shaft, groove or saw some slots in it, glue some sheet metal in, tabs in there, and give them a twist, and you got yourself an instant axial fan blade. And this is just a taped together sheet metal housing and a piece of shop rag to work as an air filter. And the reason why none of this is all nice and tidy and pretty looking is because at the proof of concept stage, it still works. So until it breaks, it stays that way. I found out my stuff lasts longer if I don't monkey with it after I get it working. The same thing on the front. I've got the shop rag around the inlet vents because the fan draws the air. And that keeps everything, all the metal chips, out of a DC motor. You don't want chips in a DC motor. It'll get caught between the armature and the magnets, or it can get stuck in the brushes and the commutator. And, well, if you're running this stuff, keep your motors filtered. What can we see in the picture here? So we have the motor here with the single speed pulley, which goes up to the first belt, which goes to the intermediate. All this crap down here, this is the box that holds the power supplies for my CNC stuff, and an old computer case. This is just the 220 wiring, which is sharing the outlet power here and the outlet strip on the front of the stand. And altogether, no problem with loads. Another note is these, if you're running your machine, a small machine like this, you're not going to run the full amperage capacity of a motor. In other words, you shouldn't be pulling breakers. Even under a heavy load, I pull maybe 8 amps on that motor, even though it's rated for 15 to 20. So you're either really geared up, or you're pushing too hard, or you've got a really dull bit. You shouldn't be popping breakers with anything near 2 horsepower on a machine this size. Over here is another stepper motor. This is kind of another goofy, I wouldn't call it an essential modification, but it does give you, or gives me anyway. So this has a pulley on it, and I have another pulley that I can slide into the back of the lathe spindle, and that is a split hub there. And when you tighten the bolt, that nut is tapered, and it just expands and locks to the inside of that of the spindle. And with the belt running from here to here, I can use that as a rotary axis for for whatever. I've used it a couple of times for hole patterns and such before I did the capability on the mill. So this doesn't get used much, but once in a while I do have a call for it, so the motor just stays there until I can find another use for it. Alright, you yeah, I did want a good fit. Using the speed reduction for the motor, because your DC motors do spin faster than an AC motor. An AC motor's speed is regulated by the number of poles that are built into the motor and the frequency of the AC power going into it. So a motor made in the USA is going to turn a little bit slower in Europe because they run 50 hertz power and we run 60, and you'll see a lot of motors have that dual rating on the nameplate. Speed RPMs for 50 hertz and the speed for 60. But with a DC motor, these typically spin anywhere from, usually starting at 4,500 RPM up to 6,000 RPM. So keeping the speed reduction in place is definitely the way to go. So I just leave that on its highest reduction, and these are the 3 speeds I can play with because that corresponds with the 3 grooves in this pulley. So those are really my main adjustments. Anyway, to change the speeds on these, I can stomp on my foot pedal. That releases the tension, and I can easily slide my belt wherever I want. And the arrangement here gives me a lot more slack to move the belts where I had to fight them off with the small amount of room that the stock adjuster gave me. So there we have the motor down there, and the motor just gets pivoted forward, which loosens that belt, which in turn loosens the other belt. So under the lathe and attached to the this crappy stand here, that black cylinder back there is one of them lifting arms for trunks and hoods, and that provides the spring pressure on the motor to tension the belts. And you'll see this wire cable here that goes around the pulley. That cable just attaches to the body of the lift support and goes down to a hinged pedal that I stomp on, and that relieves the tension on the belt, just like such. And you can see back there the motor pivoting on its hinge. So that makes for a nice, quick, and easy belt change. The long axis stepper motor is a NEMA 34, and that's just attached with this timing belt onto this bracket that's bolted to the end of the bed, and it gives like a 2.5 to 1 increase ratio, because stepper motors work better under low RPM. They have the most torque and accuracy, so by allowing this to turn slower, which seems kind of counterintuitive because I did have this reversed at one time. The big pulley was over here, thinking I would get better torque and holding power, but it turns out to be the opposite. Now you do lose a little bit of resolution because now your motor's turning fewer amount of revolutions or ticks to get a certain position, but I find I don't need a whole lot of precision on this axis anyway, and the micro-stepping seems to take care of it. But it's all set up so I can use this manually and under motor power. Occasionally I need to take the tailstock off, especially when I'm doing the foam stuff. My foam table, since my since my high-speed spindles can sit over here, I've got a lot more table travel to work with in the CNC foam shaping of the foam. So I need to get the tailstock out of the way because this table extends and overhangs over here. And a lot of times I need to take this off. And it's not heavy or anything. It's just when you take it off, the gib falls on the floor. The stupid little locking pin that goes underneath this lever here rolls away, and in my shop, once it hits the floor of no return, I never see the shit again. So this piece over here is a swivel I attached to the arm that holds the other crap on this base, and this is just a piece of angled plate, where it's got the 55-degree angles put into it, and this is just a piece of shelf paper there. And what I do is I just slap that against the tailstock there, and I can slide the tailstock onto the shelf, lock it down, and then slide that out of the way. The gib stays in place, the pin stays in place, and I don't lose no parts. And I don't have that on the floor or on a table falling over, because there's no way it's going to sit by itself out of balance as it is with the extension and the stuff on it. So that just keeps that out of the way while I'm working with something long or working with the foam, and then when I want it, I can just come back, slide it back into place. I haven't adjusted it yet for the slop of the joints, but I'll get around to that. As it is, I do this, often enough to make this worthwhile, but not often enough to make it perfect, you know what I mean? So that just stays there, and this just sits inside of a pivot there, so I can just get that out of the way when I don't want to be snagging on it or anything like that. The motor on the short axis is just a directly coupled NEMA 23. Probably not the best idea, because stepper motors, well, they have steps. Typically 200 steps per revolution. 200 steps per revolution. So to get anything in between, you have to use something called micro stepping. But the motor inherently still follows those coarse steps that are built into it. So when it loses a step, or it cogs, or it's unpowered, and you repower it back up, it locks into that nearest major step. And there's only so much accuracy you can get with that. So this really should have a speed reduction just to get the accuracy, but since I don't have the room, or at least I didn't have the room until I moved the motor, that's why it was directly coupled. But now that I have the space back there, I may change this arrangement. But until then, it works out kind of alright. As I said, it's directly coupled. Now back there, unless you get a big heavy duty one, do not use spiral motor couplers. They look nice and they feel good, but as soon as you put any kind of load on them, they will snap. I went through 2 of them, and then we just went back to putting a piece of rubber hose across there, because you don't want a rigid coupling with a really loose, sloppy machine. Because if you rigid couple a motor to something sloppy, you're going to put a lot of wear on the motor itself. You're going to ruin its bearings, and they're really close tolerance motors as they are. So you don't want to put that kind of stress on the motor shaft. So you have to have a flexible coupling. Now there are Lovejoy style couplings which have, the fingers that are meshed together with a piece of rubber in between. Even those don't have that much accuracy into them. There is going to be some play and squash. You use that kind of stuff on pumps. You don't use it on CNC. So I was using the old rubber hose thing, and it worked fine, but after a month or so, especially with the oil on it, it would start degrading and get mushy, and I'd have to change it out. Well, another method I came up with, which seems to work really good, is if you can see back there, you see there's a split sleeve, is what that is, with a hose clamp on it. And the stuff you see oozing out is the same style rubber hose I was using, which was an old air hose that I've been chopping up for the last 2 years to make these things. But so instead of having the hose itself provide all the torsional integrity being bridged across 2 shafts, I just use the rubber hose as the cushion, or the slightly flexible part, so not a rigid coupling. That split shell there clamps around the outside of the hose, which in itself clamps around the shaft of the motor. So I still have a semi-rigid coupling. I've got more accuracy than I had before, and there's no chance of that breaking. And I thought that idea worked out really well. I'll throw up a diagram of what I actually meant with that and go in a little more detail. But for those of you guys looking for a coupling solution, that may be something you can look into. Cool. So here we're just looking at a motor and a shaft. And like I said, you don't want to direct couple them because the motors are kind of fragile, and you don't want to put a lot of wear or any wear on these bearings if you can avoid it. One of the most popular couplers for CNC work is a spiral coupler like this, normally made out of aluminum, and it has spiral grooves cut in the middle, so it's like a sturdy spring. Unfortunately, the grooves are usually pretty thin, and under a heavy load, the spring will kind of unwind and snap one of the spirals, and then it just becomes an unconnected mess. So I don't really recommend those for anything on a real machine. If you're using something like a rep wrap, shop bot, something, they're probably fine, but for a load, these really aren't rated for that. There may be some heavier ones available, but then they become a lot larger, and then it gets expensive and breaks, and you either have to keep spares on hand, or your machine's down until you order another one. So I abandoned that route and just went back to the old garage job of putting a piece of flexible, this is actually a piece of airline, but any kind of a rubber or a flexible hose clamped between the two is fine, but it only lasts, depending on your machine use, about a week or a month, because the area of the hose in between the clamps is free to absorb torsional stress or rotating, where if I got a load on the shaft and I turn the motor, this is going to twist in the area in between the clamps, and twisting back and forth eventually separates the layers of the hose, or even in the case of a solid plastic like a PVC, it becomes stressed and weak and just starts becoming gummy, and you lose all your accuracy. So, but I still stuck with that for close to a year and just replaced the pieces when I noticed the accuracy going bad. So we need a better idea than that. So that went out. It was recommended to use a Lovejoy coupling, which looks like that. And that's 2 shells there with interlocking fingers, and in between the fingers it is cushioned by a rubber or a urethane spacer. I don't know what the hell they call that thing, but it's kind of rigid if you get one that's really tight fitting and you use a really dense hard material. But these really aren't suited for positional accuracy. They're, like I said, they're just for pumps and for industrial use, really. There may be CNC versions available, but I imagine they're probably kind of spendy, and like I said, just like the spirals, you're going to have to keep them on hand, or they may be hard to get. So didn't use that idea either. We'll send that away. My simple method was to stick with a piece of hose or something flexible to act as a snubber or the flexible membrane, but attaching this nose cone here that's split, and that's sized to snugly fit over a section of hose, so it acts like a sandwich. So rather than the hose being under a torsional or a tension load, it's under compressive load all the time. So the bit of hose is over the motor shaft, and then that's squeezed around it with the shell here that's been split. You get that little bit of flex to protect the motor bearings, but the accuracy is still really good, and it lasts quite a long time until your hose degrades due to oil or heat or whatever. And you got plenty of hose material options to play with, and that was just a quick and dirty method, and it turned out to be the one I'm sticking with. It's more than accurate enough for my machine. If I have the motor locked and I try turning the handle, there's no torsional play in it at all. So I'm kind of happy with that simple setup, and you might want to consider that if you're looking for a way to couple the motors. Oh yeah, the little laser thing, I forgot to show you that. Turn off the light, get this out of the way, and we'll move you over. I did feature that in one of my other videos, but I don't believe it was posted, and it was probably such a crappy job I probably won't post it. But when I have my wheel in a certain spot, and I think that's it, I can turn on the little magic light there, and that allows me to just throw something on the table or my foam table, and I can quickly find the 0 point that I've got programmed in, and I can also use it for finding bolt holes or taking measurements off of other parts. So if I want to find the center of this, well, I can just put that, get the crosshairs on there, and just do a measuring with the DRO. I can quickly find the edges of pieces and stuff like that. Neato, huh? So typically the first thing I do is get this lined up with an edge, like the table edge or the vise. So I would unlock my mill head and just bump that around until I get a sharp fall off with the laser at an edge. Excuse me, darn it, running into the frickin' camera again. You guys are always in the way. So with the laser, you're looking for a drop off. Geez, now I'm getting glare. Let me grab this. Now I got this little square here, square piece of metal. You look to see how quick the laser line drops off an edge. If it goes off slowly and at a slant, well, you'll know you're off just a little bit. But if you have it just right and everything's focused, that line will almost disappear immediately. See how that's crawling off the edge like that? But if you get to where it just goes, boom, goes away, then you're pretty darn close. And for this kind of layout I'm doing, it doesn't have to be super precise. This is mostly for foam patterns and such, where when you cast a part, your part's going to shrink and you got machining to do. This is just to an aid, a measuring aid, a layout aid. It's not really for precise measuring, but it is really nice for finding where you want to put the your bolt holes and stuff. So I take the crosshair there and I'd zero out the DRO, and then I'd have a preset offset. So if this line is already aligned with the tool this direction, I just have to do an offset going back and forth, and I think my last offset is 4.64 inches in imperial, and then I just wind the DRO, however much the offset is, and I'll be where that crosshair used to be. So it's just a little quickie layout aid, and it's come in handy a number of times. And along with that, I want to modify or do something with this base plate so I can have it locked in to a few different positions on the base stem here, the post. So that way, all it needs is a dimple or something that's not going to move once it's lined up. So I'll probably just do a grub screw in here with a point and a couple of dimples going around for key positions that I want, and that way I can just find my particular spot, dial it in, lock that down, then when I lock everything else, this will be in a line with the laser, because if you have your offset for one position, well, you move your head a little bit, now your offset is useless. So I need a way to keep my reference point the same. So that's a relatively minor thing, and I'll do that shortly when I work out the new laser mounting position. But plus, the lights look pretty cool on video. Accuracy. You're not really going to get it on this machine unless you've got to the point where your skill can overcome the adversity. The areas of play you need to address or look at is one, the gibs. Now, we already covered that. We got thin gib strips. We got really badly machined ways, and they're not accurately machined, so you're going to have tight and loose spots. So on top of that, you need to address your screw stability. So it has a ball bearing. This particular screw here has a ball bearing here, and that goes to a straight plain bearing here, and it gets sort of clamped together via this pulley, or in a stock machine would be the thumb wheel, or what do you call them damn things? Indicator collar. And there would be a shim in between the collar and this housing, and that would control the tightness of this bearing. So even after you've gotten that all set up, it can still get loose, because if you haven't looked at your machine closely, that plain bearing, that the roller bearing and the shim right against, is held in place by one stupid little grub screw on the bottom of each of these castings. There's one here, there's one under here, and there's one more. Oh, on the tailstock. So each of these has a grub screw that can loosen up. And if that inner plane bearing or block starts wobbling around, it doesn't matter what shims you have in place or how well you have this set. And that bit me a couple of times. That's why I want to point it out to you. Make sure that darn collar is snug down tight. Then dial in with your shims or whatever method you choose to lock your screw in position. Well, I hope that was enough to spark some ideas and things to look for on your own machine if you happen to be unlucky enough to possess one. What can I say? They're a great learning experience, because once you've dealt with this and got it working to your satisfaction, you can pretty much handle any other machine out there, I think. So, either way, I don't really regret the choice. I said it's been a lot of fun, been a lot of screaming, been a lot of time, but I think it's been worthwhile. Anyway, until I think of something else or my next little project, take care, be safe, stay dirty, and don't pinch your dick in a vice, or whatever saying might be going around now. Bye now.